that the diagram shows two different compounds. What is the total number of structural isomers, including compound 2, including this one? That could be formed by adding a second methyl group to the ring of compound 1. The number of pi and the number of, you have to count the number of pi electrons in each compound as well. So the question is kind of straightforward. What they're looking for is you have to make isomers, and there's a condition that what you should do is you should add a second methyl group to the ring of compound 1. So that's 1. They've already drawn 1. So that's number 1. Where did they add the methyl group? This is the methyl group. So this over here is the methyl group. This one over here that they've added to this compound. They've added one over here. Mikhail, do you understand the question?
Yes, sir. Yeah.
Okay, so what could be another one? You could add one over here, right?
Yes.
Or you could add one over here, so that's another one. Or you could add it to this one, and they were very specific that you have to add it to the ring. So you've got 4 positions where you could add. That's 1. I mean, let's include that one. So you could.
Sir, what about next state as well?
So what about this one? Can you add one over here?
No.
But you can add one over here, right? Because there's a.
Yes.
It's supposed to be, so you can add one over here. So that's 5 different positions, right? So that would be 5, and you have to find the number of pi electron clouds. So that's under the number of pi electrons. So that's 1 pi. Actually, that one is 1 pi. This one is another pi. So in a pi bond, you've got 2 electrons. This one is a pi bond. So that's a total of 4 electrons. So the answer would be D, right? Is this clear?
Yes, sir.
Wait, sir, why is it 4?
No, because see, if you have a double bond, whenever you have a double bond, you've got 1 sigma and you've got 1 pi, right?
Yes.
So sigma is a sharing of 2 electrons. It's an end-to-end sharing of electrons, right? Pi is also a sharing of 2 electrons. What's a pi bond? A pi bond is one atom has a p orbital, the other one also has a p orbital, and they overlap sideways, right? So that's a total of 2 electrons getting shared, right? Is that clear?
Yeah.
So
Yeah.
So 2 electrons shared, 2 electrons. Yeah. Yes.
It's electrons in each compound. So shouldn't it be?
Yeah, I didn't get your question. You just lagged a bit. Can you repeat?
Yeah. You see how there are 2 bullets.
Can you repeat again?
Under what is? There are 2 bullet points. Right. Second one says that number of pi electrons in each compound. So shouldn't it be like each should be 2? No.
No, you're talking about that. Like you're talking about having a total of like. He's talking about like one compound, like you in each compound. Like if you pick one compound, how many pi bonds does it have? It's got 1 and 2.
Yeah, the 2. So you take.
So that's 2 pi bonds, right?
Yeah.
So that's 4 electrons. Because I showed you 1 pi bond. 1 pi bond has 2 electrons. Is that clear?
Okay.
I said, can everyone hear me properly?
Yes, sir.
Yes.
Yes. I can't hear you properly. That's this. So, but is this point clear? Is this point clear that that's a sharing of 4 electrons, right?
Yes, sir.
If you had said how many pi bonds, that's 2 pi bonds. And a sigma bond is also a sharing of 2 electrons. So If you had 2 sigma bonds, then that would be 4 electrons as well. Now moving to the next one, he's saying which compound has the molecular formula C6H10O. So basically, this is a question about skeletal formulas. So you have to be good about skeletal formulas. So what is the answers? First thing, 6 carbon atoms. So that's 1, 2, 3, 4, 5, and 6. So that is fine for the first one. So C6. Count the H's now. So there would be 2 H's with this one. There would be 1 H. This one would have 3 H's. This one would have 2 H's. This one would have 2 H's. So let's, this one has 4 bonds, so it's not going to have any H. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this, and there is 1 O as well. So I don't think there's anything wrong with this one. So option A looks to be correct. We can have a look at the other options. They're definitely wrong then. So that's 1, 2, 3. So how many carbons? That's 6. Count the H's. This one will have 3. This one will have 3 H's. 3 H's. This one will also have 3 H's. So that's 12 H's. So that's obviously wrong. The same goes for this one. It's 6 carbon atoms. This one will have 2 H's. This one will have 2 H's. This one should have 1 H. 1 H. This one should have 2 H's. So that's 1, 2, 3, 4. How many? 4 and 8. So that's 8 hydrogens. So although it is C6H8 and O. And just for practice, I mean, the first one is obviously correct. Just for practice, 1, 2, 3, 4, 5, 6 carbon atoms. Hydrogens, that's 1, 2, 3 for this one. 2 for this one. This one should have 1. This one should have 3. This one should have 2. Each carbon atom should be making 4 bonds. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 hydrogens. So, and that's 12. There's another one over here. Or we can just write OH. So again, C6H12 and O. So only the first one is correct. Is that clear?
Yes.
Yes, sir.
Yes.
Acha, next one. Next one is about, just hold on a second. Okay, so the next one is about what is the structural formula of the major product when HBr reacts with 2-methyl butene. So he is referring to the major product. Where did we do major products? Just a second. Let's just quickly have a look at major and minor products once more. So we did do this. We did electrophilic addition, right? So we did this was the mechanism. We did talk about electrophilic addition. We did talk about the Markovnikov's rule, not in bromination, not in hydrogenation. We talked about the rule in this thing, whenever you have an asymmetric molecule getting resulting in 2 different products. So you've got an addition reaction. The rule was, like, if the double bond, what is reacting and what is getting added, there are 2 options. Either the H and OH get added in this way to the double bond, or they get added in this way, where the H gets added to the carbon at the end, and the OH gets added to the carbon in the middle. So you've got 2 products. And the major product, the Markovnikov's rule was that the H likes to get added to the carbon, which is in serial bond C, that is already bonded to more H atoms. So if one of the carbon has 2 H's and the other one has just 1 H directly bonded to it, then H and OH, the H likes to be bonded to the carbon that's already bonded to more H atoms. Is that clear? Do you remember the rule?
Yes.
Yes, sir.
Okay, so the next part is, so what is the structural formula when HBr reacts? So let's draw 2-methyl butene. Starting with but, what is but? How many carbons? What?
4.
So that's 4. So that's 1, 2, 3, 4. 2ene means double bond is on the second one, right? And then on the second, there's a methyl group. So there's a carbon. This one will have 3 H's. This one over here will have 3 H's. This one has 1 H. This one has 3 H's. So that's, and let's just, okay, so let's just focus on the double bond now. So HBr getting added. Where do you think will the H get added to, and where do you think will the H, will it get added to this carbon atom, or will it get added to this carbon atom? Which one has more H atoms? This one,
The first one on the right.
the one on the right. And remember, the H should be directly bonded to it. I'm not talking about the hydrogens of the other carbon atoms. I'm talking about the hydrogens that are bonded. So this one has no hydrogen. This one has 1 hydrogen. So the HBrH would like to be bonded. It likes to be bonded to the carbon that's already bonded to more H atoms, and the Br would be bonded to the other one, and the double bond would go away in the middle. Right? Is that clear? Okay, is this clear, everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Acha, now the next part is about writing a condensed form of this. So which one of the condensed formula is actually representing this? We know this is the major product, but which one is the correct option? So the first one starts with CH2Br, right? I mean, the end is C with 2 H's and 1 Br. We don't have that. It's C with 3 H's, C with 3 H's. So it's not, I mean, so the first one is wrong. Like at the end, or at the beginning, you don't have a carbon with 2 H's and 1 Br. You don't have that. The carbon with the Br is somewhere in the middle of the chain. As the next one, you've got a carbon and it's got 2 CH3 branches. And the same carbon, I mean, the one I'm highlighting, this one. So you have a carbon that's got, so we have a carbon. So this one and this one are exactly the same. It's got 2 CH3 branches, so they put them in brackets, and it has a Br as well next to it. So it's CBr and 2 CH3 branches, and then you have CH2. So the next one is CH2, and after that you have CH3. So the next one is CH3. So this is exactly the same as this. Is that clear?
Yes, sir.
Sir, so we have to memorize this, like that this is the major product.
You don't have to memorize this. Why do you think you should? The only thing you have to memorize this is, why do you think you have to memorize this? I mean, the only thing you have to memorize is, where does the H get bonded to? You're talking about
The carbon with more number of hydrogen atoms.
but what do you think you need to memorize? Like, because
No,
you
I
don't
mean
have,
the structural formula, so you could just like, if a question like this comes up, you just
you need
know.
to know how to write the structural formula. Like, how do you write the structural formula? That you have a carbon atom, you write what's attached to it. I mean, there are many ways of writing this. This one is, if you put anything in the branches, I mean, there are 2 ways. Like, how do you write the condensed? All of these are structural formulas. This is the condensed version. Like, if I want to write the formula in 1 line, then that's my condensed version. So both of them are basically the same formula. There's no difference between them. This is a slightly more displayed version of that. So how do you write it? The way you write it is, you start following the carbons in any order, like from left to right or from right to left. The first carbon is CH3, so you write CH3. The next one is a carbon which has Br and CH3. So you've got a carbon that's got Br and it's got a CH3 branch, so you put it in brackets. After that, this one is carbon with 2 H's. And then there's a carbon with 3 H's, right? Is that clear?
Yes. Sir, the hydrogen bonds to the carbon atom with the more number of hydrogen atoms, right?
That's the Markovnikov's rule. That's this rule that we studied. that in unsymmetric alkenes undergo these 4 addition reactions with where like HCl gets added. So you add bromination, hydrogenation. Now this was not an issue with hydrogenation because in hydrogenation it doesn't really matter where the H gets bonded because you're going to get the same thing, right? And
Yes, sir.
and it wasn't an issue with bromination because in bromination it's 2 Brs that are getting added. So it doesn't really matter which one gets bonded to which one because it's the same thing. But it's going to be an issue when water bonds or when hydrogen halides bond with it. Now the next thing is which reaction is most likely to be involved in the formation of a positively charged intermediate. Now for this, we would have to study. So we'll have to study a bit about halogenoalkanes. So let me just quickly talk about. Let's do it over here. One second, let me just. So let's talk about halogenoalkanes. We haven't done their mechanisms. So I'll just discuss those quickly. Just hold on a second. Let me open the. Now, halogenoalkanes are basically these things. They're basically any carbon chain with a halogen. Like it could be a Cl. So this is chloroethane. We've already learned how they are formed, like bromination results in a halogenoalkane. And it could be any number of, it could be a bigger chain, which might have Cl and might have Br, might have another Cl. So these are some examples of halogenoalkanes. Now I'll quickly first do the reactions, like what reactions are they involved in? So, and what are the properties? So halogenoalkanes, first thing, are polar compounds. You've got a slightly positive carbon and a slightly negative Cl. So that results in the formation of they've got a dipole. So since there's permanent dipole interaction, so they do have permanent dipole interaction, which is why what happens is that they are relatively stronger than van der Waals. As long as it's the same size molecule. Because remember, van der Waals forces, they increase with size. So you have to be careful about this same. So in same size molecules, they're relatively stronger than van der Waals forces. Hence, they have higher melting and boiling points compared to alkanes and alkenes. Compared to alkanes and alkenes, since they only have van der Waals forces. So for example, if you're given a chloroethane, then its melting point would be higher compared to a normal ethane. So it's going to be higher than a normal ethane or ethene. So we can include ethene over here. This is talking about the melting points, right? Is that clear?
Yes, sir.
Yes, sir.
So,
Yes, sir.
so let's quickly do all the reactions. So I've got a chloroethane. I mean, I've got a normal halogenoalkane. Now, basically, there are going to be 4 reactions. Let's talk about these 4 reactions where these chloroethanes can be converted into other compounds. So let's start with the first one. I can turn it into an alcohol. So this can be turned back into, it can be turned into an alcohol. So the Cl will get displaced by OH. So instead, you're going to have an OH. Before that, you had a Cl. This is known as hydrolysis. So that's the reaction. It's a reaction. It's called hydrolysis. And the conditions that are required for that are NaOH aqueous, and reflux. Okay, those are the conditions that are needed for that. And this is known as nucleophilic substitution. I'll talk about nucleophilic substitution in a bit. Then you can do the same reaction, a very similar reaction, and you can turn it into, you can turn the same thing into an amine. So it could be turned into an amine, NH2. So that's another reaction. You could do that. And the conditions that are used are NH3 ethanolic and reflux. What ethanol here simply means is, when I say ethanol, ethanolic, or alcohol is used as a solvent, it's simply, what that simply means is that water is avoided. Water is not used to prevent hydrolysis. So even if you want to dissolve ammonia, you're going to dissolve it in ethanol, not in water. Water will not be used as a solvent. So water is not used so that the above reaction does not happen, to prevent hydrolysis. Is that clear?
Yes, sir.
So ethanolic simply refers to the solvent. And there's another condition. You could also use another condition, which is, or you could use ammonia gas in a sealed container plus heat. So you could directly heat it with ammonia. So that's another one. And then you have another one, which is, again, a similar type of reaction. This other one is, anything, that's it. So this other reaction is, let's just, Just a second. Yeah, that's fine. Now this other reaction is the Cl gets replaced by the Cl gets replaced by, let me just copy paste. So in this other reaction, you got a Cl again and it gets replaced by a Cn. And that's basically, so that's basically your reaction. And it gets replaced by, so the halogen gets replaced by Cn. The conditions that are used for this specific reaction are, you use NaCN ethanolic or KCN. And again, it's ethanolic. Remember, we did discuss why ethanol was used. Plus reflux.
Sir, could you repeat why it's used?
Yeah, I said water, because water is avoided, because if you use water, then there's going to be hydrolysis. Instead of the Cl, there's going to be OH ions coming in the way. Is that clear?
Yeah, yeah. Okay.
So water is not used to prevent hydrolysis. So this reasoning goes over here with this one as well. To prevent just hold on a second. Okay, so there are three reactions. The reaction is simple. You've got Cl replaced by OH. Similarly, Cl getting replaced by NH2, Cl getting replaced by Cn. Now, this last one has some significance as well, that that whenever nitriles are formed, one thing happens: the carbon chain length increases. So formation of nitriles, because a lot of times you want to increase the carbon chain length. Let's say if there's a 2-carbon atom molecule, you want to turn it into a 3-carbon atom molecule. That's what you're going to do. You're going to add a nitrile. So formation of nitriles, it lengthens the carbon chain. Is that clear as well?
Sir, can we use KCN as a catalyst?
Ek cheez, remember this thing, that make sure you remember this, that there's no difference between NOH and KOH. They're kind of the same thing. There's no difference between NaCN or or KCN. If there's NaCl or KCl. So remember, Na and K are kind of interchangeable. Like potassium dichromate 6 and sodium dichromate 6 are kind of the same thing. Is that clear? Because the sodium ions and the potassium ions are spectator ions. They're just there. They don't have any role in this reaction. Is that clear?
Yes.
Yes, sir.
Okay, so formation of nitriles lengthens the carbon chain, and so that's why this reaction is important. And there's a fourth reaction. These ones are known as nucleophilic substitution. All of these reactions, they're known as Sn reactions. They're known as remember, there is substitution. We did talk about the type of reaction. So this is substitution. A Cl is getting substituted by another functional group. So it is a type of substitution, and the specific name for this is nucleophilic substitution. We'll discuss nucleophilic substitution in a bit more detail later. So all of this comes under nucleophilic substitution. All of this. So let me just put it. So all of these reactions are nucleophilic substitution. Now there's another reaction which is known as an elimination reaction, which is that you can turn a halogenoalkane back into, you can turn it back into an alkene. What will happen is, this is known as an elimination reaction. So that's known as an elimination reaction. The conditions that are used for that are NOH ethanolic. And again, it's reflux. So those are the conditions that are used. And what happens in this case is that your molecule, this is exactly a similar reaction, which we had earlier studied as well. What would happen is that the halogenoalkane would lose the Cl from one of the atoms. And at the same time, it would also lose an H as well. So it will lose the Cl from one atom and it will lose the H from the other atom, and it will turn into an alkene. So this thing will turn into an alkene. So this is gone, and the double bond is going to come back into the molecule. So alkenes are formed. Plus there's going to be a byproduct, which is in this case would be HCl. Is that clear?
Yes, sir.
Yeah.
So alkenes are formed, and you'll also have HCl getting. So you also have HCl getting formed along with it. And remember, watch out for cis trans. And we had discussed a similar reaction that carbon is lost from. So remember, halogen is lost from one atom. And H is lost from adjacent carbon atom. So if the halogen is somewhere in between, so H is lost from adjacent carbon. So if the halogen is somewhere in between or in some other position, then the double bond could be on either side. And you have to watch out whenever you have alkenes formed, you got to watch out, be careful about cis trans, watch out for cis and trans. They would be counted as separate molecules. Is that clear? Because we did a similar reaction somewhere. We did dehydration. Did we do dehydration of alcohols? We talked about cracking. Just 1 second. We did the oxidation of alcohols. I don't think we did dehydration of alcohols, but leave that. We'll do that later. So anyways, coming back to this. So is this all clear? This is halogenoalkanes. 3 reactions, 3 substitution reactions, and you got 1 elimination reaction. Is this clear?
Yes.
Yes, sir.
Okay, now the next question is, let's go back to the question. What was the question? The question was about the mechanism of the reaction. So it was specifically about the mechanism of these reactions, nucleophilic substitution. So if I go back to the question, he's saying which reaction is most likely to involve in the formation of a positively charged positively charged intermediate. So it's a halogenoalkane which has bromine, and there's dilute NaOH being added. So positively charged intermediate. So basically, you're talking about the mechanism of the reaction. So we would have to discuss the mechanism of this reaction, which is nucleophilic substitution. So let's discuss the mechanism here. And remember, we're discussing the mechanism of nucleophilic substitution. And let me just double check the syllabus as well, just to confirm how much of nucleophilic substitution is left in the new syllabus. Just 1 second. So term associated with nucleophilic, we did that. Describe the following substitution reactions. Fine. Of in ethanol. As in leave that, we'll do that later. So Sn1 substitution, including the inductive effect of alkyl groups and so on. So let's and also Sn1 secondary halogen mixture of two. Fine. And the difference of the reactivity produces alkenes. We did this one that it produces alkene. So let's do the mechanism now. So it's basically pretty much the same. Now the mechanism, there are two mechanisms. And again, this one is describing the nucleophilic substitution mechanism that we just studied. Substitution. And this is about the mechanism. Now, nucleophilic substitution is all about halogenoalkanes, and there are three types of halogenoalkanes. There's a primary, there's a secondary, and there's a tertiary halogenoalkane, just like alcohols. So you've got a primary halogenoalkane. It's got halogen, alpha carbon. Remember the carbon on which the Cl is bonded. It will be bonded on two sides, or sometimes on three sides, by hydrogen atoms, and only on one side you've got a carbon chain. Then you've got a secondary halogenoalkane, which is going to be similar, but it's going to be the alpha carbon would be on three sides bonded to a carbon chain. On two sides, sorry. And then you have a tertiary halogenoalkane. What would happen in that case is that the alpha carbon, the one that has Cl, would be bonded on all three sides by a carbon chain. So the focus is on Cl. So the first one, it's got so the first one, this carbon atom, and this carbon atom. So this one is primary. This one is secondary, and this one is tertiary. Is that clear? Do you guys is this thing clear?
Yes.
Yes, sir.
Yes, sir. Yes.
Okay, so one carbon chain, this one has two carbon chains, this one has whatever the carbon chains is, we don't, or whatever the types of carbon chains, we don't care. But you've got primary, secondary, and tertiary. Now the primary one, the first one, has a mechanism known as Sn2. So primary halogenoalkanes. Their mechanism is known as Sn2 mechanism. Now the S stands for substitution, N stands for nucleophilic. So it's an Sn2 mechanism, this one. Let's write it this way. It's Sn2. Let's write it in that order. N and 2. So Sn2 mechanism. And remember, S stands for, I'll also add that. S stands for substitution. And N stands for nucleophilic. So primary halogenoalkanes. So I'll just discuss quickly, or maybe I'll just write the whole mechanism. What will happen is very quickly. So we just have a couple of minutes, and we'll talk about it later. So this is my primary halogenoalkane. Let's say there's a Cl, and there are 8 atoms attached to it. So the carbon has a pretty strong positive charge because there's a Cl that's right next to it. Is that clear why this bond is polar? Is this clear?
Yes, sir.
Yes, sir.
Okay, so the carbon Cl bond is like really polar. So the next thing that will happen is you've got 3 nucleophiles. OH minus 1. Let me write it the other way. OH minus 1 is 1 nucleophile. Why is it a nucleophile? Because it's got a negative charge. What's a nucleophile? Nucleophile is anything that's attracted to positive charge. So it is definitely attracted to positive charge. There are 2 other nucleophiles. You've got NH3. Why is NH3 a nucleophile? Because N has these lone pairs. And you've got Cn minus 1 as a nucleophile as well. So these ones these are the other nucleophiles that you should know of. Where did we learn about these nucleophiles? Because the reaction happens with either NaOH or with NH3 or with NaCN. So it's Cn minus 1, OH minus 1, or NH3. So you've got 3 nucleophiles. The end result is pretty much the same. So the mechanisms are kind of exactly the same as well. So you got an OH minus 1 coming in. What will happen is the OH minus 1 would be attracted to the carbon that's positive. The electrons in this bond will be repelled because Cl wants to take away those electrons. Cl is very electronegative. So as the OH minus 1 comes in, it gets attracted to the positive carbon atom. The Cl electrons, they get repelled by the negative charge over here. So they get pushed away. Is that clear? Is this clear? Yes or no?
Yeah.
So what's the next step? The next step is the OH comes closer to the it comes closer and closer to the carbon, which is positive, and starts to form a weak bond with it. So its lone pairs are really attracted to the carbon, and as the OH approaches it, the Cl starts to leave. It gets further and further away, and its electrons, they become further and further away because they are being repelled. So eventually what will happen is that the electrons of Cl are going to be, they would eventually leave and break off, and the OH would come in and join up. So the next step is remove the negative charge over here because so the overall charge on this thing is -1. And the final step is that the Cl leaves or gets knocked out because of repulsion. So the final last step in this entire process is that the Cl just leaves with the electron. So you got a Cl which is -1 now. And the OH has come in and it has joined up with this carbon, which was positive. So the OH has now taken its place. And that has resulted in the formation of an alcohol. So you got this entire reaction scheme. And let me just quickly, and you have to memorize this entire thing. I mean, it's easy to understand, but you have to memorize, you have to remember the fact where the partial positive should be drawn, where should be the negative charge, how would you draw the curly arrows, which represent the movement of electrons. So everything has to be shown in a lot of detail. So the reaction is pretty simple. OH minus 1 gets attracted to the positive carbon atom. Where did the OH ion come from? It came from the NaOH aqueous that you added. And as it approaches, the Cl starts to get repelled by the negative charge on the OH. So it eventually gets knocked out, and that's a simple reaction scheme. Is that clear? Yes or no? Is this clear?
Yes.
Yes, sir.
Yes, sir.
And this middle thing is known as a transition state. Now, transition state is different from an intermediate, which means that you never actually get this thing. It's a one-step reaction. I mean, this entire thing is a one-step reaction. Unlike an intermediate is actually formed in the reaction. This is just transitioning, like the OH ion approaching and the Cl leaving, that's it. So, I mean, you're just imagining that there's this state where the OH ion comes in and the Cl gets knocked out, right? So it's like a hypothetical state because you're never going to get this in the mixture. This is a highly unstable state. So it's just for a brief instant, for a temporary millisecond or microsecond or a nanosecond, this thing might have formed in the middle of the reaction. So the entire reaction is a one-step reaction. So remember this in detail and about recall. Just a second. Make sure 2 depend on the structure. Don't forget that. Okay, so I'll write the mechanism for the other ones as well, because they weren't very specific whether you wanted for OH ions or NH3 or Cn, but the other ones are kind of the same. But is this clear?
Yes, sir.
So let's continue with this in the next class. We'll do the Sn2 mechanism, Sn1 mechanism as well, sorry. So this is Sn2. And then we'll discuss why are the 2 mechanisms different. So this is specifically for primary halogenoalkane. One thing that you would realize is there's no carbocation getting formed. There's no positive carbon atom. So if you go back to the question, where's the question? The question was about formation of a carbocation. Where did our question go? So this question over here, it was talking about a positively charged intermediate. So it's definitely not a primary halogenoalkane. They're not talking about a primary halogenoalkane because the intermediate that we have in our case, it's actually a negative ion. It's not a positively charged, and it's not even an intermediate. It's a transition state. It's some hypothetical state that probably got formed when the transition happened. It's a one-step reaction. Is that clear?
Yes, sir.
Yes, sir.
So let's continue with this tomorrow then. Okay.
Okay, sir. Allah Hafiz.
Okay, take care.
Okay, sir.
Okay, sir.